Question 2 asks, what value smoothing capacitor is required across the 100 ohm load of figure 1 in order to achieve a ripple voltage of 0.3 volts peak to peak? What assumptions have been made in order to arrive at an answer? Estimate the power dissipated in the 100 ohm load with this value of C connected. Assume that the transformer and the diode are ideal. So we need to draw out figure 1 again, and I'll do it in black because the poor old blue pen's struggling. And we've got VS is 9 volts RMS, and this is still 100 ohms. And the question wants to know about a smoothing capacitor across here to smooth the voltage value. So the capacitor is going to be like that, and this will be our V out. Okay, well, let's draw the waveform that's going to be involved in this. We'll have nothing, conduction of the diode, and then a longer period of nothing, or same size period of nothing, and then conduction of the diode, and so on. Okay, that's fine. So what about the output voltage? So this is V out, and this is time. So output voltage, well, it's gonna capacitors. If this was the first ever cycle, let's assume it's not, but if it was, you get a voltage output that looks a bit like it would lay on top of the black line, but I don't want my green pen to turn black. And then like that, and so on. But we're going to assume firstly that this isn't the first event, that there have been many of them beforehand. The second thing we'll assume is that the ripple shape is triangular. So we'll say this has happened before, so our output in this region, even though we don't know what happened over to my left, we can still say, well, this happened before. We get to the middle point of that, and we charge up immediately, and then we discharge, get to the middle, charge up immediately, discharge. And this ripple shape is triangular, and the question is asking us to seek a situation where the height of this ripple is 0.3 volts peak. So this distance here is 0.3 volts, and that is peak to peak because that's a peak and that's a peak. So we can say that for a capacitor, I is equal to C dV by dt, and we can say that the load current will be 9 times root 2. This is the peak load current. I is V upon R, so it's upon 100, and this is also equal to I. So we can solve the capacitor equation for C, and we'll have I dt upon dV is equal to C, and we can sub in the I as well from here, so that will give us 9 root 2 over 100 times, now the dt is between the charging event, so that's 20 milliseconds, which is there. And the dV is the distance we're going to do the discharge, the voltage that we're going to allow it to discharge over that time period, so that's 0.3 volts. So that's what C should equal, and we'll have 9 times root 2 upon 100 times 20 e minus 3 divided by 0.3 is and this is C is equal to 8.4853 millifarads. So that's 8,485.3 microfarads if you prefer. So that's how that one's done. The only thing you really need to know are the equation for capacitor, as the differential equation between voltage and current in a capacitor, which I think we did in lecture 1, and Ohm's law. And you have to know how to apply them obviously as well. So then the next question asks, what's the peak power dissipated in R? Or what's the new power dissipated in R? So under this situation, you can attack it by several ways, but the way I would do it is to say there is an average value here, and that will be in the middle of the ripple bit. So if we say that the peak minus half the ripple is the average voltage of this green triangle, which is our new output voltage. So we'll say, where can I write it? I'll write it down here. So now there's no working out done there. That's a judgment that you make, and as long as you write your assumptions down and they're reasonable, you will score credit for them. So if you derive answers that are based on those assumptions, then it all follows through anyway. So the averaged value of the smoothed waveform is, and then we've got the peak value minus half of 0.3, so we'll say it's VPK minus VR upon 2, which is, it's 9 root 2 to get the peak, (12.72) minus half of 0.3, 0.15. So that leaves us with 12.57. 5.7, and it's actually 8 because it's 779, so it rounds up to 8. So we can do V squared upon R now, and we're saying that this value always exists. So the power is volts, and the power is equal to V squared upon R. It's not 2R anymore because we're not worried about the half sine wave. This is a constant value that we're assuming. And I think it's a fair assumption because we spend half the time below the line and about half the time above the line. So overall, it'll even out. So we'd have 12.578 squared upon 100, which is 1.582 watts. So the other solution was for the capacitance, and we used IT upon C and the Ohm's law for the resistor. So that's an S. So that's how we go about question 2.